Hi everyone. If you don't know me, my name is Ryan, and the entire purpose of my channel is to help you pass the FE Mechanical exam. Today I'm going to go through the solution to this problem. You can solve this problem with me interactively using the first link in the description below for free, as well as all the other problems that I solved in my FE exam playlist. I recommend you go ahead and try out those problems to just give yourself a refresher and be ready for problems like those on test day. I hope you went and tried those problems. Let's get into the solution now. It says a ball is launched with an initial speed of 800 miles per hour at an angle of 40 degrees above the horizontal. What is the radius of curvature of the trajectory at the peak of the motion? Okay, so we transferred it to a clean sheet of paper. So let's write down some of our givens. The first one is that we know the launch speed is 800 miles per hour. Let's call that V naught, as well as the angle theta. The launch angle is 40 degrees from the horizontal. What we're looking for is the radius of curvature at this peak point. That kind of, at the peak point of the parabola there. The radius of curvature is what we're looking for. If we think about some of the relationships that we might recall relating to radius of curvature, the first thing that comes to mind here is that the acceleration is the rate of change of speed in the tangent direction plus speed squared over the radius of curvature in the normal direction. That's the first thing that comes into my mind. You can see that radius of curvature term kind of pops up in the denominator there. One thing that we know about this motion is we fully know the acceleration, right? We know that acceleration vector is a constant value and it's pointing downward in the negative j hat direction if we define the unit vectors like this. And this magnitude is equal to the acceleration due to gravity, g. So we fully understand the acceleration. If we kind of sketch out the tangent and normal unit vectors here at the apex, what we see is that the acceleration is fully normal at that apex point. It has no tangential component, right? It's always pointing downward. So that means that the speed squared over the radius of curvature, or the normal component here, is equal to the acceleration due to gravity. So if we rearrange, what we know is that the radius of curvature is equal to v squared over g. Only thing we don't know now is, what is v? V is the speed at that apex point. And some things that we know about the motion are that at its peak, when that kind of displacement here, the total height, let's call it sy, when that reaches a local maximum, what that means is that the derivative of sy in time must be equal to 0. The derivative of sy, or the displacement in the y direction, is equal to the speed in the y direction. The most fundamental relationship for velocity is that it's the speed in the tangent direction. If we look here, if the speed is to be only in the tangent direction, that means that there can be no y velocity component. So this kind of aligns with what we expect. If it must be fully in the x direction, we think about, are there accelerations in the x direction that could have caused changes in that speed? And there is no acceleration in the x direction, right? We said it was all in the y direction. So if the acceleration in the x direction is 0, that means that the speed, or the time rate of change, the acceleration is just the time rate of change of speed. So that must mean that the x component of the speed is equal to a constant value. And if it's constant, has the same value that it had initially, we can kind of sketch out that initial value here, which is this. This is our Vx, which is just equal to V naught cosine of theta. Okay, so if we go ahead and plug in right here, this is equal to V naught cosine of theta, this entire term squared over g. Okay, so if we plug into this, we'll be able to get to the solution. If you're enjoying the video thus far, please go ahead and leave a like and subscribe. It really helps out the channel. I would appreciate it a lot. Okay, let's get right back into it. So what we have to work out now is just the units here. We have V naught cosine of theta, this entire term squared, divided by g. We know that the initial speed is 800. The cosine of 40 degrees is what we use. We're going to square this entire term and divide it by gravity. In the English system is 32.2. So the numerator is in miles per hour. That's going to be squared. The denominator is in feet per second. If you recall, the choices were all in miles. So let's go ahead and convert the denominator here. The radius of curvature is equal to 800 cosine of 40 degrees. We're going to take that and square it, divided by 32.2. We're going to multiply this by 5280 over 3600. And the final unit is going to be miles. What we get from this calculation is rho is equal to 4.75 miles. Let's go ahead and check this answer. Okay, if we click view explanation here, we'll see some references here in these bubbles. These bubbles which are located kind of here. Page 103 and 101 of the reference. So let's go ahead and check those out, see what kind of references they had in the solution. On page 103, we see reference of this normal and tangential components. That's the kind of idea we used when we wrote out the acceleration. That's the only thing that we could recall in terms of the radius of curvature and what kind of formulas involve that radius of curvature. No, in the reference manual, there's also this formula with the radius of curvature, but we'd have to know a relationship between y and x for the height and the horizontal displacement, which we don't know and would take a lot of time to find. Our method that we use, we're able to solve this problem in essentially one line. Okay, so there was that reference, as well as another reference was on page 101 of the reference manual. That's when we were looking at the particle kinematics, just understanding that at the maximum height, we know that the speed is going to be equal to 0. We also understood that the vertical acceleration was equal to a constant value. It was at minus g. And we knew that there was no horizontal acceleration. The acceleration was 0, which means that the speed was equal to a constant value in the x direction. Just quickly kind of walking through what we did. Fundamentally, we realized that the acceleration is just the rate of change of speed in the tangent direction plus the speed squared over the radius of curvature in the normal direction. We kind of drew out the tangent and normal unit vector directions. We noted that the speed is pointing only in the tangent direction, and the acceleration was pointing only in that inward pointing normal direction. Using that the acceleration was pointing downward, we were able to realize that we could just equate gravity to that v squared over rho term. Solving for rho and solving for the speed at the top, which we knew was fully horizontal, and it was equal to v naught cosine theta, we were able to find the final answer here. The final answer of 4.75 miles, corresponding to choice A. If this video was helpful for you, please go ahead and leave a like and subscribe. Thanks for watching. I'll see you in the next video. Goodbye.